take some questions on the Gaussian lab. I had a few people catch me in the hallways asking questions about some of the results that you were asked to get. So let me get through a few slides, then I'll take questions. We'll do a Kahoot on the Gaussian, and then I'll finish things up. There's a lot of material in this lecture about the different methods that you'll use. But in terms of our lab, we just used the 6-31G basis set and the B3LYP or density functional theory. But I wanted to kind of give you a resource to go to when you do Gaussian later for your research or working with, like if you go into integrated lab, you'll need to do some Gaussian calculations. So I just wanted to give you a bit of a foundation as to what all this alphabet soup means, 6-31G, what is all of that? These commands and basis set definitions are really small because this goes back to the 60s when the first computers were around. Everything was on punch cards. And so you couldn't have very descriptive names for things because you would just waste time making all those punch cards. If you could get by with letters and numbers, the shortest possible designations, then you did that. Because you actually had to individually punch out the binary codes for all the letters that you were sticking into the machine. So did y'all see the Hidden Figures? You know, that big computer that she was working on, that was a punch card computer. So she had to make the punch cards and load a stack of cards into that computer, and it read the program in, and then it executed it. So if there was one punch that was not done right, the whole program could crash. So it's very, very tedious. So the beginnings of these, this whole approximation is a great simplification, and that is to be able to separate the motions of the nuclei from the electrons. And this is just an illustration. No matter where this construction worker moves, those bees can keep up. And so really, from the perspective of the bees, the person's not moving at all. Because no matter how that person moves, they're moving very slowly. Just like we're on the Earth, and the Earth's flying through space, but we don't feel it. Everything we do is relative to the Earth, and to us, the Earth is not moving. So in Gaussian, we can tell the software where the atoms are, and they're fixed in space, and then the calculation determines where the electrons go. And it's calculating the electron cloud. That's why another name for these calculations is called the electronic structure calculation. And then what it does is it moves the nuclei, and then it redoes the whole calculation. And so most of the time you're doing a geometry optimization where you're moving the nuclei to find the minimum energy so that you can optimize that geometry. So are the angles in water really 109.5? You know, that's our assumption using Vesper theory, and you will build the molecule with that assumption, but then Gaussian will calculate the positions of the electrons, and then it'll relax that structure, and that angle will increase just a little bit. So it's a good initial guess, but the actual minimum energy structure for water is different. So this is a very important approximation. It allows us to simplify things. Remember the Hamiltonian for the particle in a one-dimensional box. It was just one dimension, it was in X. This has a lot more dimensions to it, and there are a lot more things in a molecule than just one particle confined to a certain axis. You know, we have nuclei, we have electrons, we have attractive potentials. For in a particle in a box, the potential is 0, but in an atom or molecule, you have a positive nucleus, you have negative electrons. And so in this particular Hamiltonian, we have the nuclei here denoted by the Greek characters. So these are the mass of all the nuclei, and you're summing through all of the nuclei and calculating the second derivative of those nuclear, the kinetic energy of the nuclei. And then we have, for every nucleus, we have the repulsion of all the other nuclei. So we pick a nucleus and we calculate the repulsion of all the other nuclei because we know the positions of them in space. And so this is a nested loop, and that's what computers are made to do. It just cycles through these calculations. And then it's for every nucleus. Oh, we also have the attraction here. This attraction here. And you pick a nucleus, and then you cycle through the electrons. And so you say this is the attraction of the electrons to this nucleus, and then you pick a different nucleus. This is the attraction term for all the other electrons to this nucleus. And so you have a nested loop for the attraction term. You have an attraction term here. Actually, both of these are the kinetic energy terms. This is the kinetic energy term for the nuclei. This is the kinetic energy term for the electrons. And then we have the potential energy term. This last term here is the one that makes life difficult. It's the repulsion of all the electrons to all the other electrons. But the electrons are moving so fast and have such a flexible wave function that we have a difficult time treating them as discrete particles. We really have to treat their wave nature. And how do these waves interact in this complex surface of a molecule? So that's the term we actually don't have good math for. So we can't really treat the electrons as discrete particles in space when they're dealing with a molecule. So this sort of complex dance that the electrons do with each other is called electron correlation. And that's a very difficult term to solve for. We've come a long way since our single particle in a box Hamiltonian. So these are the same pieces of the Schrödinger equation, but one's for a molecule, one's for a particle in a box. So what Gaussian is doing is starting with what you give it, the nuclear coordinates, and then it's calculating the electronic structure. And it does this with various model chemistries. So these are the model chemistries that you can select from. And we'll talk through these very quickly. There's molecular mechanics, semi-empirical. You can read the list there. So let's go through these individually very quickly. It's just sort of background information for you. So if we can't deal with the electrons interacting with electrons, and we really don't want to do all of those nested loops of all those electrons, we could just ignore the electrons altogether and come up with this sort of attractive and repulsive potential called the Lennard-Jones 612 potential. This just is optimized to, we've got a couple of factors here that you can optimize. You have sigma here and this epsilon, and you can adjust that to produce the average bond length for, say, a carbon-hydrogen bond, or even like two molecules bumping into each other from different ends. Like you might have a molecule that has some steric hindrance where they're bumping into each other. You'd have an optimum distance between two hydrogens that are not bonded to each other. And so that might be a van der Waals distance. And so what you do is you have a table in your computer of force field values, which is these Lennard-Jones parameters. And it goes through every nucleus and says, okay, what's my distance to hydrogens? What's my distance to other carbons, and so on? And it's very fast because you're just looping through really two loops, two distance measurements. You're not dealing with any electrons or really any wave functions. So this is the fastest. We can do proteins, full up proteins with this method. So if you've got a ton of atoms, this is the method that you want to use. So for polymers, DNA, proteins, etc. Some of the examples in Gaussian are the amber force field or the universal force field, UFF, and that's the one I use. Then we have semi-empirical methods where we can, again, simplify the calculation by getting rid of the core electrons. Notice when you add another atom, you bring in a whole lot more electrons. You're just adding one more atom, but you're getting a whole lot more electrons. Compare the calculation with fluorine, which has 9 electrons, to the calculation of chlorine, which has 17 electrons. So even though the chemistry for fluorine and chlorine is going to be similar, they're both halogens, chlorine is going to take a lot longer to calculate if you're calculating those core electrons that really aren't doing anything chemically. So all you can do is just take away those core electrons and reduce the charge on the nucleus. And you've saved a lot of time. Just deal with the valence electrons, and that's what semi-empirical methods do. So they're very fast. They have what they call effective nuclear core potential. So they're just reducing the charge on the nucleus and dealing with the valence electrons. And they have those in like larger orbitals, so it can treat chlorine's size, but it'll just reduce the charge on the nucleus. This is, again, for different types of atoms. This is going to be, they're going to have different core potentials for different types of atoms. So what's a different type of atom? Think of a carbon in an SP situation where it's bonded to 2 things versus bonded to 3 things versus 4 things. So it's got, those are the 3 types of carbons that don't break the rules. Now, what would be a carbon that does break the rules? Think of carbon and cyclopropane. So cyclopropane is a cyclic molecule with 3 carbon atoms, and those angles are 60 degrees. Well, that's even tighter than 90 degrees. And there is no SP type, SP, SP2, SP3 that has a 60-degree angle. So semi-empirical methods for cyclopropane, they'll work, but the values are going to be off. The energies are going to be off. So. Now, ab initio and density functional methods, they have 2 pieces to them. One is the theory piece that estimates the electron correlation, and the other is the basis set piece. The theory piece, we'll go through the list first. The Hartree-Fock method just ignores that electron correlation piece. So in the Hamiltonian, you have the kinetic energy for the nuclei and the electrons. You have the attractive potential of electrons to electrons, the repulsive potential from the nuclei to other nuclei, and then the electron-electron repulsion, they just ignore it and just don't do that calculation. You say, well, that's crazy. You're going to be really off in your calculation. Yes, you will. But if you think about it, you're doing reactants and products, and you're off on your reactants and you're off on your products, and you're doing delta H or delta G calculations, you're going to be off by similar amounts. And so the difference will be fairly accurate. So we can still do fairly accurate calculations ignoring that electron correlation because the errors cancel if we're taking differences. We can add in some higher terms to the Hamiltonian and kind of correct for that electron correlation. So that's what MP2 methods are for, but they're very expensive computational time-wise. They take a long time to do, like maybe 10 times longer than the Hartree-Fock method. So if you have 1 hour calculation, this adding MP2 makes it a 10-hour calculation. And you might get an improvement of 5%. So is it worth getting 5% more accuracy with 10 times the cost? And it may be, but you're going to pay for it. Configuration interaction explores the different effects of different electron configurations. You can put electrons in the higher unoccupied orbitals and the whole molecule. It's basically the calculation of the electron cloud becomes more accurate when you explore the unoccupied orbitals. And then the one we will use, or we did use in lab, is B3LYP. That stands for this density functional. It's a set of functions that describe the whole electron cloud, not just individual wave functions. And then we need a basis set. So these are levels of theory. These are ways to overcome the electron correlation problem. And so I guess that's the take-home lesson. Level of theory is how you deal with electron correlation, because we can't calculate it explicitly. And then the basis set is, I would say, the amount of freedom an electron has in the molecule. So we treat the electrons individually, but what we'll do is, instead of calculating the electron position relative to the other positions in the electron, we'll reduce the charges of the nuclei in the model from all of those other electrons. So we'll calculate this electron's wave function by reducing the charges on the others. So we'll shield the other nuclei with the other electrons, and then we can calculate this electron's wave function. And that's the Hartree-Fock theory. The basis sets, this is the smallest basis set, STO3G. So if you want the fastest calculation, other than molecular mechanics and so on, if you wanted the fastest ab initio, or from initial calculation, an explicit calculation of the Hamiltonian, this would be the smallest basis set. It has just the normal electron orbitals that you're used to. The 1s orbital on hydrogen, that's all it has. The 2s and 2p's on carbon. But we can add more orbitals to give the electron more freedom. Like, think about hydrogen bonding. The electrons surrounding that hydrogen are kind of in a straight line. They're not just spherical, they actually have a direction to them. So it might make sense, if you wanted to model hydrogen bonding, to give p orbitals to the hydrogen, to let that electron take advantage of some 2p orbitals. It might only mix in 10% of that 2p orbital, but it might lower the energy for the molecule. And then if we take those, basically take these Gaussians that we're modeling these electron orbits with, we can just add more and more functions. Let me show you this graphically. The analytical radial distribution function, or the radial wave function, is shown here in blue. So that's the actual mathematical formula. It's e to the minus r. It falls off with e to the minus r. But that has to be calculated numerically. So they have to loop through, like you did in the spreadsheet, every row of the wave function. Like you have to divide it into a grid, and then you have to calculate the wave function, the first derivative, the second derivative, row by row, and however fine you divide that box. And that takes a long time. If you could just assume that those wave functions were Gaussian in shape, then there's a quick analytical result. You don't have to do the numerical integral. You can just calculate the integral and the derivative of the Gaussian functions. But this is a Gaussian function. The Gaussian function is not as pointed at the top. You see that? And so we need to add a whole bunch of tiny Gaussians that have a narrow width to larger Gaussians that have a wider width to match this blue curve. And so that's what we're doing with these basis sets, is we're adding more and more Gaussian terms so that we can match the actual wave function distribution. Okay? And it's still faster to add 4 or 5 extra Gaussian functions on an atom if we don't have to do the numerical integration or the numerical differentiation. Now, higher angular momentum, this probably has the largest effect on your calculation and making it more accurate. And that would be like putting p orbitals on the hydrogen or d orbitals on the second row atoms. They don't have access to d orbitals. They'd have to go up to the 3d orbitals to get those. You can add 3d orbitals onto carbon to give it a little bit more flexibility. Why would you need that? Think of cyclopropane. So cyclopropane molecule is very difficult for carbon to only use its p orbitals. It really needs to use some other flexibility. These electrons don't know math. They don't know that they're supposed to only sit in a p orbital. Okay. If you give them a little bit of d orbital character, then they'll take advantage of it and they'll mix all these functions together. They're going to do what they do. Now we are trying to figure out mathematically how to describe their behavior. And so we've come up with these spherical harmonic functions. And those spherical harmonic functions are the s, the p, the d, the f orbitals. And we're trying to figure out how much of this function we could use and how much of that function we could use to model what the electron's actually doing. So don't get so stuck in your mind that this electron has to be either in a 2p orbital or a 3d orbital only. The electron can do whatever it wants to do. And we're trying to figure out which mathematical function gives us the answer that nature is giving us. So we're trying to model nature using these functions. And so if we give it a little bit of 3D character and it doesn't need it, it won't use it. It won't mix it in because it's not needed to get that natural answer. But if we do give it some 3D character, and like a cyclopropane, it needs it, it will use some of that and say, look, if you give me 3D orbitals, now I can match a 60-degree angle. The bottom line, if this is confusing the heck out of you, give it a whole bunch of stuff and it'll be more accurate. Give that electron more freedom. Because in nature, the electron has all the freedom it wants. Okay. So this is how you would designate it. Like 6-31G would be the basic root, and then you could add in D, comma P, and that would put D functions on all the elements except hydrogen. And then because there's so many hydrogens and like hydrocarbon molecules and so on, you can save some time by leaving these extra functions off of hydrogen. So you could have 6-31G and then just put the D in parentheses, and that really gives you a lot of flexibility. But if you want to go ahead and add P orbitals on the hydrogens, you need to put a comma P. So it's in that order, heavy atoms, and hydrogen. So in Gaussian, a heavy atom is anything other than hydrogen, because it was written by physicists. Have you seen the physics periodic table? Yeah, so the physics periodic table is this. So this is hydrogen and then helium, okay, all the way up maybe uranium. So it's got all the elements, but basically that's the most important thing is hydrogen. So they call everything else a heavy atom. So hydrogen and the heavy atoms. Okay, so it's we could also, if we went a large electron cloud, let's say we have anions. Anions are larger than cations. What's the simple reason for that? Can anybody tell me? Why would anions be larger than cations? Yeah, electrons don't like each other. You put an extra one on there, and they the whole cloud expands. What do you think about cations then? They're going to be more dense, yeah, smaller. So again, the nuclear charge hasn't changed. You pull an electron away, and now the electrons can get closer to those nuclei. So these diffuse functions can be added in front of that G. A single plus puts a larger s orbital, like it allows it to put like the next sized s orbital on there, and on the heavy atoms first, and then the second plus will put them on the hydrogens. Okay. So this is a crazy one here, monster basis set. Got extra Gaussian functions on the valence electrons. We've got extra diffuse functions, and then we've got a whole lot of functions added to our orbitals. We've added f orbitals on the heavy atoms, and we've added d orbitals on the hydrogens. So why, I don't know. But again, the more freedom you give the electron, the more accurate your structure is going to be, and the more accurate your vibrational frequencies and so on. So this is a nice little summary table. So 2 to 100 atoms, you could use that sort of industry standard basis set. For anions, you want to add diffuse functions. Transition states, you may want diffuse functions as well. You definitely want some polarizability or polarization functions added on. For large systems, 2 to 2,000, or like the Jerome, I don't know if you know Jerome, his system has 250,000 atoms. Okay, yeah. And so he's doing molecular mechanics on this protein for Dr. Haynes, and it has 250,000 atoms in his little screen. And he's got 2 like super powerful graphics cards, and they're actually doing the calculation on the graphics cores. So they have like a couple of thousand graphics cores that are doing these calculations. It still takes a few days to calculate. And so that's sort of a review. If you've got molecular mechanics, these are the keywords you would use. I use UFF, semi-empirical, PM3, or now they have PM6. The density functional theory, this B3 LYP, or I've heard people they're calling it B3 lip, 3 lip. That seems like a person has 3 lips. That's really strange. But B3 lip, 6-31G with a D, and then you always compare molecules with the same model chemistry, because if you're trying to compare, one of these B3 LYP calculations with something that's semi-empirical, they're using totally different methods for the electron cloud, and so the results are not comparable. Essentially, you can't increase the level of theory all the way up to perfect and increase the basis set all the way up to total freedom for the electrons, because your calculation time would go to infinity. But you can see when the trend the improvement kind of dies out on basis set, and you can see when the improvement in electron correlation kind of dies out, and you can get to a sweet spot, which is a really good approximation of the full Schrödinger equation. You guys got some experience with the GaussView, building the molecules. Were there any questions, or any difficulties you had with GaussView? Yes?
So one of the questions for the lab was, why is the geometry point group is not correct in benzene?
Yes.
And I had a kind of hard time figuring out the answers. So
Yes.
I was just wondering, what's the answer?
Yes, so on that one, it doesn't take much to ruin the point group when you're building these molecules. If that benzene molecule, if the hydrogen is off 1/10 of a degree, then it doesn't have that rotational symmetry. And so it's real easy to build a molecule, and to you it looks symmetric, but when you do the calculation, it might come in C1, which is basically no symmetry at all. You have C1 means you have one symmetry element, and that's identity. So there's no symmetry in a C1 point group. Or sometimes it'll get CS, which CS just has a reflection plane. So it has two elements, identity and a reflection plane. So CS is very common as well. For benzene, you might get C3, no.
I got CS or C1.
You might get D3H if it was like cyclohexatriene. So if GaussView builds this molecule, it doesn't know about resonance structures. These are going to be short bonds. These are going to be long bonds. And so you don't have a C6 axis if the bonds are different lengths. Okay. Now, one thing that's interesting is that GaussView will show these double bonds, single bonds, and so on, but this is a really troubling thing to say to you, okay? These little sticks don't exist.
They're not double bonds?
Yeah, that's right. The electron cloud is the thing that's holding this molecule together. We taught you as freshmen, and this is a really good tool to use, to think of a bond as a stick between two atoms, and that there's two electrons right there holding those two atoms together. Okay? And it's so ingrained. I mean, you're like a fish, and this is the water you've been swimming in. You ask a fish if they're wet, they're like, what are you talking about? Right? They've never not been wet. They don't even know. And so you've been swimming in the water of these sticks actually holding the atoms together. And so sometimes when you do a calculation in Gaussian, especially with an atom like a chlorine that wants to get kind of far away from the molecule because it's so darn big, it'll show the molecule, but there won't be a stick connecting the chlorine to the carbon. And you panic. You're like, something's wrong. My chlorine's not bonded to my carbon. Well, if you measure the distance, and you can do that in GaussView, you click the measure tool, 2 atoms, it'll give you the distance. If that distance is like 1.7, 1.8 angstroms, it's bonded. That's a typical bond distance, so it's bonded. It just didn't draw the stick, because it's got a little table in there somewhere in the software, and it says, oh, I've got a bond distance that's this. Oh, that's a single bond. It looks in the table. Oh, this bond distance is a little closer. That's a double bond. So it's just looking up these distances, and for your benefit, drawing some sticks on the screen, because that's what makes us feel nice and warm. Okay? But if your sticks don't quite match what you're expecting, okay, like if you have a molecule with 2 chlorines on it and they're next to each other, they're cis, and they don't like each other, and they get a little too far away, GaussView is going to say, oh, those aren't bonded, when they really are. It just doesn't have a very accurate lookup table to say, yeah, that's a chlorine-carbon bond. It might be a little longer. I'm going to go ahead and draw that stick. Okay, so it's pretty easy for it to mess up the point group. Now, there is a symmetrize. Well, let me go ahead and escape out of this. Well, I don't want to get sidetracked on this because I want to do the electrostatic potential stuff. So let me do that quick. There's a button on there. If you hover over the buttons or look at some of the menu items, you'll find one that's called a symmetrize.
It's in view.
It's what?
It's in the little view tab.
View tab. Okay, so come up here and you can view and.
What? Calculate. My bad.
Let's see.
Okay, never mind.
Maybe edit.
There we go. At the bottom.
Yeah, and so since we don't have a molecule built, we can't symmetrize anything, but you can go in there and you can tell it, I want this molecule to be D6H. And it'll force it to be D6H, and so that's fantastic. Okay. Now sometimes symmetry is your enemy. If the structure is going to break that symmetry when it's optimizing, it'll kill the calculation. So sometimes you want to do the calculation with no symmetry, other times you want to do it with symmetry, but those are finer details. Let me go back here and we'll zoom ahead a little bit. So you guys built the molecules, set up your jobs, and ran them. These are the calculation times on TATB. This is a molecule that I did research with. I found that it has 300 basis sets if you set up the calculation with like P3OIP, 6-31G with polarizability functions on the carbons. You can go back and see what this would have cost, even back to like the first polyatom 1967 calculation. It would have taken over months. Now we can do it under 5 minutes on the previous version of Gaussian. But then on this previous version of Gaussian, with this kind of 3 gigahertz Pentium 4 computer, I had a calculation that took 2 weeks. So this 2 weeks of CPU time, so it was slightly more than 2 weeks actual time, because I had to write to disk. And this was on a part of a polymer, and my student babysat the computer, and I mean, after a week and a half, you're really nervous, because if you get a power outage, it's done. And so we finally got this geometry. It took 2 weeks. And so if you take this same function here, this same time function, and go back to 1967, it would have taken 1,500 years. That's kind of like Doctor Who type stuff, right? So in 1967, if you had this time function, you could say, wow, if we try this calculation now, it won't be finished for 1,500 years. But if we just wait 30 years or 40 years, we can do it in 2 weeks. It's weird, isn't it? It's like, wait, what do you mean it's going to, so whenever you hear people say, with current technology, hold your wallet. Because they're probably trying to scare you about something, and most of the time they try to scare you in order to get your money. That's just my own personal thing. But we never stay at current technology. When have we ever done that? So it's just something to consider. You hear that all the time. With the current trends, blah, 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 blah. Okay? And there's a lot of panic right now, and all that panic is over that phrase, with current technology or with current trends. So, okay, so this is what Gaussian's doing. It's going through this optimization step where it's calculating the slope of the wave function energies and so on with respect to the coordinates, and it's changing the geometry and seeing if it's at a minimum. Eventually it reaches a minimum. And then you do a frequency calculation. So this first top piece is the geometry optimization. And then we go into a frequency calculation, and it's possible, although I don't think with any of your molecules, that you would be at the top of a hill in the molecule. So it's trying to find the minimum, but it might find, like if you've got eclipsed ethane, when those hydrogens are going across each other, if you built eclipsed ethane, it might successfully minimize the energy and stay in that eclipsed form. But if I twist that molecule this way, it goes downhill. And so the frequency potential for all those other motions, like the bond stretches, that frequency potential goes up. And so the vibrational frequency is in that harmonic potential. But what if it goes down? What if the potential is upside down? Then relative to that spot, the vibrational frequency would be negative. And they call those imaginary frequencies, because in order to get that, you take the square root of this potential and you get a negative number. Okay, an imaginary number. The square root of a negative number is imaginary. And so that's why we call these negative frequencies, we call them imaginary frequencies. And so if you see those negative frequencies in your frequency output, then you've got to figure out what motion is at the top of the hill. And it's probably a twist in the molecule, like a methyl group that needs to twist. You twist that methyl group by reducing the symmetry, and then you go back into changing the geometry, and you redo this whole thing. You get a new geometry, you do the frequency calculation, and now you don't have any negative frequencies, and so now you're finished. You have the optimized geometry and the energy data for that molecule. So this is the standard practice for coming up with energy for a particular molecule. And you did all this with acetonitrile and benzene and chlorobenzene, and it probably worked well because those molecules are pretty rigid. They don't have any way to really twist. So then after the calculation, you can simulate the spectra. We'll teach you how to do that next. We can do these surfaces and explore the electron cloud. And this is where we have some fun. So the ESP, or Electrostatic Potential Map, the ESP map, is a really good tool. So let's look at some of these. So this is the electron density surface. And so you have these different ISO values. You know, up here we have one that looks like it's calculated with a 0.0004. So that's calculating 99.96% of the electron cloud inside that surface. Looks like this one is a 0.05, so that's just a 95% surface. So 95% of the electron density is inside that surface. If you go down to 0.8, so 80% is inside there. So 80% of the electrons are that close to the nuclei. Then you go to 60%. Oh, let's see what we're doing. No, it's 1 minus that. So 20% of the electrons are there. 40% of the electrons are there. 95% of the electrons are inside there. Okay. And notice that 95% surface looks a lot like the space filling model. The space filling model was just made with sort of the van der Waals radius of the atoms. And so the atoms really don't change that much character when they bond in a molecule. The electrons go over the whole surface of the molecule, but the sizes of the atoms are still somewhat preserved in the molecules. So if you have a big bromine atom and you stick it on a molecule, it's still going to be big. You know, these tiny little fluorines, you put them on there, they're tiny. And so you can see this interesting thing here, the total electron density. This is a mesh model. So we're plotting those 95% electron density surfaces on here. And you can learn some things. Look at HF. The hydrogen's on the right, the fluorine's on the left. But then look at lithium hydride. So lithium's on the left, hydrogen is on the right. Isn't that cool? Even just looking at the size of the electron cloud, you can see there's more electron density on the hydrogen than there is on the lithium. So lithium hydride, that's why we call it lithium hydride. We use the IDE to indicate that the hydrogen is negative. And then HF, we call it hydrofluoric acid because it's, or hydrogen fluoride, the IDE indicates that the fluorine is negative. Now, if we take a positive charge and we walk along that density surface mathematically, we can see when that positive charge is repelled, so that would be a positive region, and we can see where that positive charge is attracted, that'd be a negative region. So we can calculate the electrostatic potential or force on that particle. So we just go through this whole surface and we map it out. What's the force on this positive charge? And if we map that on the electron density surface, we'll find red indicates negative potential, blue indicates positive potential. So here's a benzene, and the hydrogens are blue, and the electrons in that ring are negative. And so you could see this, and you can look at this particular molecule and say, all right, if I have an electrophile, where's it going to attack? So if I have something that's electron deficient, like a boron atom, it's going to be attracted to the top of that ring. If I have something that's a nucleophile, it's going to be aiming at something positive, it's going to strip a hydrogen off that molecule. It's going to avoid the ring. And so this was the reason why I would love for a student to go through P-Chem right after Chem 2 and then take organic. Because can you imagine if you knew about the electron cloud and were able to do these calculations, how much more sense your reactions would make. But no one will take me up on that. And so it would be a sort of an experimental cohort of students, probably like 20 students, and grab them out of Chem 2 and run them through P-Chem and then enter them into organic. And it'd be tough mathematically, you know, but it would be something, I think, it would turn them into great organic chemists because they would totally get it. They would understand bonding, they would understand electron behavior in the nuclei. So that would be fun. So here's the electrostatic potential for benzoic acid. You got a positive hydrogen, negative oxygens, Mostly neutral, as green is in the middle. And so these electrostatic, or ESP maps, I call them, are fantastic. You can also look at delocalization of charge. See this resonance structure where you can move that charge around the ring? This is what we do with Lewis dot structures. For Gaussian, it just calculates the whole electron cloud, and you can kind of see the distribution of those bonds spread all the way around. It's still pretty well located on the amine, or up there on that carbon, but you've got some distribution. So here, but that positive is in that carbon. You see that it's not quite negative there. It's more negative here and there. And those carbons always have a strong amount of electrons on them. But if you twist that structure, now you've broken the ability to delocalize that charge. And so the twisted structure is much more negative on the ring, and the positive charge is located on that carbon. Now, is this a stable structure? No, but you can do things that aren't stable in Gaussian. You can calculate transition states and hold them there and then calculate their electronic structure. This is something you could not do experimentally at all, probably, or if you were, you would be an amazing experimentalist in holding molecules and making them do exactly what you want them to do. But it's very easy to do this kind of thing in Gaussian. Okay, I had hopes of asking some Kahoot questions on the electrostatic potential maps. We're going to have to do that next time because we're out of time. So Friday, be ready to do a Kahoot. Get here on time so that you don't miss it.